Okay, am I audible?
Yeah,
Yeah. Okay. So today we're going to start the regression models, learning about regression models. Probably we will complete linear regression model and also all the basics that are needed to cover linear regression, logistic regression, and non-linear regression stuff. So we will start today with understanding what is probability and what is likelihood. So we all know we already have seen a normal distribution and calculating the using the normal distribution. We already learned about calculating the probability of um, whatever parameter that is falling between a particular range, right? So given if you look at this particular diagram right over here, this is to right? So this is what probability is. What is given to us? We were given with mean and the standard deviation. Mean is the value at which the probability would be the highest. I mean, the count of the parameters would be the highest. Basically the probability would be high at mean, and it would spread on both the sides based on the standard deviation, right? So uh, for a given, this is the curve, which this is a normal distribution where mean is given as 32 and the standard deviation is given as 2.5. So in this case we were asked to probability uh, probability of a person weighing between 32 and 34 grams, right? So if you're asked to find out the probability, the weight of a mice whose weight falls between 32 to 34 grams, what we basically do, we already learned this stuff. We will just take the area under this curve, right? We use some z score tables and all that stuff to easily calculate, right? So we have seen standardization where we convert any normal any you know like normal distribution to a standardized normal distribution where mean will be equal to 0 and standard deviation will be equal to 1 using z score. And then we have that z distribution table using which we will easily get the value of the area under this normal distribution. We already have studied all that stuff, but I'm just revising again because I just want to tell you what is the difference between probability and likelihood. So this is what probability is. So what we just calculate, if we are asked to calculate the probability of a mice weighing between 32 and 34 grams, we just calculate the area under this curve. Okay. And now if you're asked to find out the probability of a mouse weight greater than 34 grams. So these parameters are constant here. The mean remained the same. The standard deviation also remained the same. That means the distribution would remain the same, but only that got changed is what is on the left side. So now we are trying to find out the probability of mouse weights greater than 34 grams. So this is 34 in the graph. So if you want to find out the area, I mean the probability, what we just have to find out, if we are bothering about 34, right? So this is 34 here. So this is 34 grams. So if you want to find out the probability greater than 34, we have to find out the area under the curve. As it is greater than 34, we have to find out the area from here to end of the curve. So that is how the probability will be calculated. And this is how, given a normal distribution, this is how the probability will be calculated. Probabilities are just the areas under the fixed distribution, right? So the distribution is constant here. In both the cases, the distribution is constant. What is just changing? The way the the probabilities of different weights in this case are, uh, that's what we are trying to find out, right? Okay. Uh, now, so now what we have changed, this part is what we are changing. We are changing the left hand sides. Okay. Now coming back to the likelihood, let's understand what likelihood is. So likelihood, if you given the same thing, so the likelihood, if you observe the probability and likelihood, the distribution parameters are on the right side here. Okay. probability of a mice weight between 32 and 34 grams given mean is equal to 32 and standard deviation is equal to 2.5. Here the distribution parameters are constant. Whereas if you look at the likelihood, here the mean is given as 32 and standard deviation is given as 2.5. Given these distribution parameters, we are trying to find out the mouse likelihood of a mouse weighing 34 grams. That's what we are trying to find out, right? So now distribution parameters are given, and then we are trying to find out the mouse weighing 34 grams. So this is 34 grams here. And now if you want to find out the likelihood, just find out the value uh, relevant on the screen. I mean, on the graph or on the distribution. We just have to find out the value on the distribution for that particular given weight. So that is called as likelihood. In this case, the likelihood is 0.12. Okay. So the likelihood of mouse weighing 34 grams is 0.12. So given the mean is equal to 32 and standard deviation is equal to 2.5. Now again, the right hand side remain the constant. Mouse weight is 34, but the distribution got changed. When the distribution got changed, what would be the likelihood? So now the mean, now the given distribution parameters are mean is equal to 34 and standard deviation is equal to 2.5. So now the, the right side part is constant. The distribution parameters are changing when we are calculating the likelihoods. Okay. And now if you calculate the likelihood of this particular thing, so this is 34 grams and the mean is also the mean is also 34 grams. So we will get the maximum value here, right? So that is how you calculate the likelihood. That is the difference between likelihood and the probability. In the probability, the distribution parameters are constant, and we would like to calculate the probabilities by calculating the area occupied within the required uh, uh, within the required constants. Whereas in the likelihood, the distribution parameters will change, but what will remain constant? The value on the x-axis, which is the weight of the mouse remained the constant, but the distribution got changed. So that is what we calculate using likelihoods. Likelihoods are the y-axis values for fixed data points with distributions that can be moved. We are moving the distribution. Okay, we are moving the distributions, but we want to find out the likelihood of a fixed data point. Okay, that is how we calculate the likelihoods. That is the difference between probability and likelihood. Um, okay, so going back to the next screen, calculating the maximum likelihood. Now we understood calculating the likelihood, right? So what we do, how do we calculate the likelihoods? So we change the distribution and then we calculate the likelihood. Likelihood is nothing but the y-axis value, right? The y-axis value is nothing but the based on the distribution and the counts, we get the y-axis values. Okay. So these are basically the values on the y-axis, the value on the graph at that particular x-axis value, right? So that is what y-axis values are. Okay. Now, why do we have to calculate likelihoods, and what is maximum likelihood is what we are going to understand now. So you understood how to calculate likelihood. Like if you look at this particular diagrams here, we are trying to calculate the likelihood of mouse weighing 34 grams. For this distribution, we got something around 0.12. For this distribution, we got somewhere around 0.2. So the mouse on the the right side remain constant, whereas we are changing the distribution. When you are changing the distribution, the likelihoods are changing. But what we are trying to find out in maximum likelihood is we will try to find out what is the maximum possible likelihood for that particular data point. So we keep on changing the distributions, and we would like to find out the likelihood where it is maximum, or at which distribution parameter values the mouse weight, the likelihood of the mouse weight is maximum is what we are trying to find out in maximum likelihoods. So that is what maximum likelihood means. Where at which distribution parameters values the likelihood is maximum is what maximum likelihood calculates. Okay. So the goal of maximum likelihood is to find out the optimal way to fit the distribution to the data. So in maximum likelihood case, just a second. Okay. So in maximum likelihood, what we actually do is we will try to calculate the maximum likelihood, maximum likelihood value. Like how do we calculate that is what we're gonna see today. See now the goal of maximum likelihood is to find out the optimal way to fit the distribution to the data. Like suppose if you take this particular example here, if you look at this particular data set given over here, and we have some distribution taken over here where the mean is residing somewhere over here. If you calculate the likelihood at this particular point, so we are getting some likelihood value, right? So if we know by just looking at this distribution, we can say this is not covering all the points. This is not the uh, right distribution that fits to this data, right? So whenever the distribution fits to the data in the right way, we will see the maximum likelihood. That is the reason the maximum likelihood, the goal of the maximum likelihood is to find out the optimal way to fit a distribution to the data. So the likelihood would be maximum when the distribution fits the data correctly. Okay. When you go through the examples, you'll understand about this more. But just now, what you have to understand now is that maximum likelihood aim is to, um, okay, so the goal of maximum likelihood is to find out the optimal way. It's to find out the optimal way to fit a distribution to the data. Okay, so there are lots of distributions available. One is this is called as normal distribution, which we frequently talked about, and this is exponential distribution, and this is called as gamma distribution. Okay, so these are just for you to understand the different distributions. So for most of the times, we just worked on the normal distribution, but the data can be distributed something like this and also something like this. Okay, coming back to this maximum likelihood part. So what we have done here is that what parameters that we need to do for a normal distribution, we need mu and the sigma, which is mean and the standard deviation, right? So these are the parameters that we have to find out to draw a distribution. So if you know mean, we know where the highest, the peak of the distribution uh, will be there. So when you know mean, you know that, and when you know the distribution, you can draw a graph by using the no, like sigma, which is like deviation, like standard deviation. Like if the standard deviation is low, the peak will be high. When the standard deviation is high, the distribution will look something like this. It would spread more. That is what standard deviation basically is. Now in the first phase, what we do is we fix sigma. Okay, and then we calculate mu. So let's see, how do we fix sigma and calculate mu? That tells us the maximum likelihood value for that particular mu. Okay, so now this is the distribution given to us. This is the distribution given to us, and we have taken this value as the mean, and the standard deviation we have set that to 2, right? Standard deviation we set that to 2, and this is the mean value that we have taken. And when we calculated the likelihood, for now don't bother about how to calculate the likelihood and all that stuff, but let's suppose we calculate the likelihood by using this distribution where sigma is equal to 2 and mu is residing somewhere here. And when we calculated the likelihood, this is the value of the likelihood. Okay, and now what I am doing is I'm shifting the mean to different values on this uh, weight axis. Okay, I'm keep on moving the distributions to the right side. When the mean is here, this is the distribution. When the mean is here, this is the distribution. And this is the mean, this is the distribution. And when you calculated the likelihoods, these are the likelihood values. Okay. But when this is the mean, okay, when we shifted the curve to the left side, and when we set this value as the mu, and this is the this is the likelihood that we have got. And when we keep on moving this to leftmost side, the values, the likelihoods are getting decreased, right? Okay, so we want the location that maximizes the likelihood of observing the weights we measured, right? Um, so what is our intention with maximum likelihood? We want the location that maximizes the likelihood of observing the weights that we measured. That means if you take this particular distribution, this is where we got the right distribution, right? So if you look at this, most of the data points are covered here. That is the reason the likelihood is more here. Okay, so now you can say that by looking at this graph, where the value of likelihood is more, this is the value at which the likelihood is more. The corresponding mu value is this. So now this is how you get the value of the mu. Okay, so this mu value indicates this is the maximum likelihood value for mu, and this value tells us that the distribution had fit the data pretty well. That is what basically maximum likelihood value means. Okay, it fits the distribution correctly. Okay, when compared to all other all other normal distributions, the distribution with mu value as this had fit the data more appropriately. So that is why we will get the maximum likelihood value here. Similarly, and now we have fixed this sigma, and then we fix this sigma and we shifted the standard, I mean the normal distributions to the right side to different mu values, and we have calculated the likelihood at each mu value, and at some point, and at a particular mu value, we got the highest likelihood value, and that highest likelihood value indicates that that particular distribution represented the data very well, or had fit the data very well. That is the reason why we got the maximum likelihood for that particular mean. So now we got the maximum likelihood, and that value will be set as the mu, will be assigned to the mu. And in the next stage, what we will do is, and so if you look at this now, this is the I separated, I mean I got all these graphs removed, and we finally got the value of the graph relevant to the maximum likelihood for the mu. So this is the graph with the maximum likelihood value for mu, with sigma set to 2, right? Sigma is set to 2, and this is the maximum likelihood value for mean. What does this means is that this location for the mean maximizes the likelihood of observing the right weights what we measured. Okay, maximizes the likelihood of observing the weights we measured. So if you look at this distribution, it covered almost all the weights. This graph exactly represented our data. Here at this phase, we have the highest number of weights, and when we keep on moving forward from the mean, the weights are getting decreased, and they became rare when we approach to the positive infinity and negative infinities. Okay, if you take the graph here, it doesn't represented the data very much, right? So the concentration is more here, but it is saying the concentration is more here, right? Because this is the mu value with the previous distribution. So the right distribution is this one, because this is the where we got the maximum likelihood. And um, now what we will do is, once we got the mu value, we fix that value, and now we try to find out the sigma value. Earlier we fixed mu, we fixed sigma to 2, and we found out mu, the maximum likelihood value for the mu, by shifting the curves from left to right. We calculated the likelihoods at different mu values, and we found out the maximum likelihood value for the mu. And when we got the maximum likelihood value for mu, that represents that particular mu value, uh, uh, I mean the normal distribution spreading around that mu value represented the data very well. Okay, and now once we got the mu value, we fix that mu value, and then we keep changing that sigma value. Okay, now again, now if you look at this, the mean is fixed here. but we are changing the standard deviations, right? The standard deviation for this is more when compared to this green line, and the standard deviation of green line is more when compared to the red line. When we decrease the standard deviation, the peak will increase, right? Because the curve will become more steep. When we increase, when we increase the sigma value, or when we increase the standard deviation, we get a curve something like this. It spreads very vastly from the mean. That is what standard deviation basically means. So now what we do is we calculate the maximum likelihoods for different sigmas now. Okay. For different standard deviations, we calculate the maximum likelihoods. I mean, we calculate the likelihoods and we take the value where the likelihood is maximum and we call that as maximum likelihood. Now, this is the maximum likelihood value for the sigma, right? Now we have found the standard deviation that maximum is the likelihood of observing the weights that we measured. Okay. Now, this is the maximum standard deviation. Okay. And now we got the maximum likelihood value for the mu and also the maximum likelihood value for the sigma. And if we draw a distribution using those two values, we will get a graph that exactly represents the data. Or we can say this is the right fit for the data. Okay. This is the normal distribution that has fit to the data by using the maximum likelihood estimations for the mean and standard deviation. Okay, this is how we we draw a graph, or we derive the distribution parameters um, by doing iterative, by fixing the value of sigma. You iterate the mu values and calculate the likelihoods, and wherever the likelihood is maximum, that value will be assigned to that particular parameter, whether it is mu or standard deviation. You will set that value and that distribution will exactly fits the data. Okay, now let's see how do we calculate the likelihoods for a given point. Okay, now we know, like, some way we represented that in graph, and these are the likelihood values that can be calculated for different data points. So uh, So this is again what we have so far discussed. To solve the maximum likelihood value for the mu, we treat sigma like it is a constant, and then we find where the slope of its likelihood is equal to 0. That means if you draw a graph for all these points, wherever the slope will be equal to 0, that is the maximum likelihood value for that particular curve. These are looking as discrete values. When we keep on, when we measure for continuous, I mean, when we keep on measuring for different mu's, you can draw a continuous graph. When you use multiple normal distributions with different mu values, okay, with very minute changes. That means if you look at this particular graph, they are very discrete at very random positions. We shifted the mu and then we calculated it, but you don't want to miss any. I mean, the bandwidth cannot be that large. Maybe if there is a maximum likelihood over here, you will miss that value. So the you has to be, like, like very close, or mu has to very close to each other. You have to keep on shifting the graph to very less change in the mu. So when you do that, you will get multiple points very close to each other, and when we join all these points, you will get a graph like this. Okay, this graph actually means is that if you have measured, this is my mice weights, and I consider this as a mu, right? I got the likelihood here. This is the mu likelihood, something like this. So I choose mu to be very small intervals. Okay. When the intervals got increased, these values will look to be continuous. And when we join all these points, you'll get a distribution like this. So to get the maximum likelihood value, you have to take derivative of this function. And wherever the slope will be equal to 0, that value will be the maximum likelihood value. Similarly, you do the same for standard deviation as well. You take multiple standard deviations with very less changes. Let's suppose if you are taking mu as 2, mu is equal to 2, and then take mu equal to 2.1 or 0.1, 2.02. When you decrease this size, you will get more values in the likelihood graph. And then when you draw a graph, when you join all those points and take a and consider the value at which the slope is equal to 0, that will be the maximum likelihood value. Okay, so this is how you calculate the maximum likelihood values for mu and sigma. And what does maximum likelihood specifies us? That gives us the right fit for the for the data. So those parameters will let us know what are the right parameters or right distribution parameters that represents the data that we have captured. Okay. Now, if you look at this, how do we calculate the likelihood for a normal distribution is what we have to understand now. Calculating the likelihood for a normal distribution. So we all know the probability density function. We already discussed about this, right? So this is the probability density function of, and this can be represented by f of x is equal to 1 by the root of 2 pi sigma square e to the power of minus of x minus mu whole square by 2 into sigma square, right? This is how the normal distribution curve will be represented. This is called as probability density function. Okay. At any given x value, it gives us the probability density at that particular function. That essentially means that the value at that on that particular graph, that is what the probability density function gives us. We already learned all this stuff, right? Now, we were given with this, when you're calculating the likelihoods, the data point will remain the same, but the distribution parameters will change. When the distribution parameters are changing, we calculate the likelihood at different values, and wherever you get the maximum value, that will be set to the distribution. That value will be set as the distribution parameter, right? So that's what we have said. Here sigma is fixed, mu is changed, mu keep on changed, right? And then we calculated the likelihoods at every point, and now wherever you get the maximum, that will be set as the mu value for that particular distribution representing this particular data. Okay. Now, if you come back here, now if I'm given with 1 point, which is 32. So if I'm given with, let's suppose, to understand calculating the likelihoods, I'll just take only 1 point right now, and the value of that point is 32 grams. Now x is given as 32 grams, right? Now I want to calculate the likelihoods. Likelihood is nothing but it is the probability density function, the value on that graph. So how do we calculate the value under that graph? Using the probability density function. What is the formula for probability density function for a normal distribution? It is 1 by root of 2 pi sigma square e to the power of minus x minus mu whole square by the 2 into sigma square. Sigma can also come outside as there is a square root. Now you know mu value because these are distribution parameters. You know sigma value, and also you know x value for this data point. If you substitute all those values, x you have to substitute as 32, mu you have to set as 28, and sigma you have to set it as 2. That's what it is done here. Point is 32, mu is 28. Okay, so x is set to 32, mu is set to 28, sigma is set to 2, and sigma is set to 2. When you do that calculation, the likelihood that you got is 0.03. Okay, and now you do a shift in the mean. Okay, now the point remained the same, but the distribution got shifted to little right side. So earlier the mu is here, now it shifted to here. Okay, now what is updated mu value? It is 30. Standard deviation remain the same, because when you calculate the mu, when you're calculating the maximum likelihood for the mu, you keep sigma as constant and you find out the maximum likelihood value for the mu. Once you got the maximum likelihood value for the mu, then you will come back, change fix the mu, change the standard deviation, and find the maximum likelihood for the standard deviation. So that is how you get mu and sigma. That gives us a normal distribution which represents the data. That is the distribution representing the data which we are interested in. Okay. Now what I have done, I have like standard deviation is kept constant and mu is shifted a bit. Earlier it is 28, now it is 30. Again, calculate the likelihood value. Okay, using this particular formula. So we got this as 0.12. In the first case, we got 0.03, and then in the second case, we got 0.12. So this is the maximum likelihood. We keep on calculating that for different mu values. At some point, you see that decreasing again, and the point from which it started decreasing, that is considered as the maximum likelihood. This is how you calculate the likelihood of a given weight or a given point. Okay, it's just using the probability density function, because likelihood is nothing but the probability density value at a given point. So how do you, if you want to find out the probability density at a given point, you have to use the probability density function, which, and for normal distribution, this is the probability density function. So this is how you calculate the likelihood for normal distributions. Okay. Earlier you have just done with only one point, right? Now let's see how do we calculate the normal distribution for two given points. Now you are given with two weights. One weight is 32 grams and one other moist weight is 34 grams. And you are also given a normal distribution with mu is equal to 28 and sigma is equal to 2. Okay. So this is not given. You started with 28 and you kept sigma is equal to 2. And you keep on changing the mu to find out the maximum likelihood, right? So we started with mu is equal to 28. Now, when it is only one data point, you use the probability density function, right? Now for this, you calculate the probability density function on this, probability density and the function on this. Now, what is given to us? We want to calculate the likelihood value where the distribution parameters are mean is equal to 28 and standard deviation is equal to 2, given one of the points is 32 and the other point is 34. Okay. So now if you look at this point is independent to this point. Weighing this mice doesn't depend on weighing this mice, right? So this mice weight would be independent from this mice weight. So this mice will not affect the weight of this mice. Those two are independent activities, right? So those two are independent measurements. So likelihoods will eventually will become just the first point likelihood multiplied by the second point likelihood. Okay. Um, so that's how, if you have n points, it would be just like if you are trying to calculate the likelihood of mu is equal to 28, sigma is equal to 2, given x1, x2, x3, so on, xn, it would be just likelihood of x1 multiplied by likelihood of x2 multiplied by likelihood of x3, so on, because these events are independent to each other. These weight measurements are independent to each other. So if you're given with 2 points, they both are independent to each other. So what do? You just multiply the likelihoods for both of them. So again, apply the same formula for this. 1 by the root of 2 pi sigma square e to the power of minus x minus mu whole square by the 2 into sigma square. You know every value to calculate that particular function. I mean, to apply to that particular function and get the probability density. So you get some value for this, you get some value for this, multiply them, and you'll get the you'll get the required likelihood for both the points. So if you're given with 3 points, as I told, so 32, 34, and 30 are given to you. Now, again, it's just a multiplication of all the likelihoods. Okay. The first point, likelihood of first point multiplied by likelihood of second point multiplied by likelihood of third point, because they are independent measurements. All the events, all the points are independent of each other. Okay. That's the reason they will be just likelihoods will become just multiplication for each other. So every data point is independent. So one data point, one mice weight will not impact the other's mice weights, right? It is not a disease that is something which will impact the other mice, or which can infect other mice. These are weights. Weights are independent parameters. So when you calculate the likelihoods, it will be just multiplication of likelihoods. Okay. So now we have seen the theory so far, and we found out that when you want to calculate the maximum likelihood, you just have to take you have to find the point where the slope is equal to 0, right? Now let's see mathematically how to actually achieve that. Okay. Now when you're given with when you want to calculate the maximum likelihood values given n points and the distribution parameters are mu and sigma, it is nothing but likelihood of each point, like likelihood of x1 multiplied by likelihood of x2, so on, likelihood of xn. Now what we do, this is the likelihood function, this is the probability density function, and using this probability density function, we calculate the likelihoods. Again, substitute the parameters x1, mu, sigma, and for xn, it will be xn. For all the points, mu and sigma are constant. Okay. Now, what is our goal here? Our goal is to find the maximum likelihood, right? How do we calculate the maximum likelihood? Um, so in the earlier cases, what we have seen, we have shifted mu, we have kept sigma is equal to constant, uh, picked the different values for mu and calculated the likelihoods, and we found out where the likelihood is maximum. And we picked that particular, we picked the relevant, when the likelihood is maximum, we pick the relevant mu value and set that mu value or the mean value to that as the distribution parameter, right? Now let's see how do we do that mathematically. Okay. So now what we have to do, given any function, if you want to find out the maximum value or the minimum value, what you do, you just take the derivative of the function and equate that to zero, right? When the double derivative is negative, that is maximum. When the double derivative is positive, that is minimum. We already studied all these basics earlier in the first sessions only. Now, given a function, we want to find out where this function is maximum. It's as simple as this, okay? But we have to find out two parameters. These are two parameters that we're trying to find out, right? So what we do is we take the derivative. How do we take the derivative? We take the derivative of mu with respect to mu, and when you're taking the derivative with respect to the mu, you're keeping the sigma value as constant, right? Because you cannot calculate both the values at the same time. You have to consider one value as constant and then take the derivative of the other value and find out where that particular value is maximum and use that value, and then in the consequent steps fix that mu value and calculate the sigma value. So that's what we do. In the first, we take the two different derivatives of this equation. So given any function, if you want to find out the maximum or minimum values, we have to take the derivative of that function and equate that to zero. Okay. And then calculate the values. Okay. And if you want to know whether that function is maximum or minimum, you have to go for the second derivative. Okay. In this case, what I'm given, this is my likelihood function. I know what is my likelihood function. And now I take the derivative with respect to mu with sigma is equal to constant. We can find the maximum likelihood estimate for mu by finding where this derivative is equal to zero. We already know that. And the other derivative will be with respect to sigma where mu is equal to constant. Okay. In this case, we will find the maximum likelihood for mu. In this case, we'll find the maximum likelihood for sigma. We can find the maximum likelihood estimate for sigma by finding where the derivative will be equal to zero. Okay. So we take where the derivative will be equal to zero. But before we take any derivative, we take the log of the likelihood function. Okay. Why we are taking log of the likelihood function before taking any derivatives? The reason is for mathematical simplicity. If you apply the log to this, the mathematics will become very simple. The calculations will become very simple. Instead of taking the derivative of this big long term with different multiplications, it is critically very tough. You can just give it a try. If you look at this, these are x. If you consider this is x1, x1, x2, x3, and if you're taking derivative with respect to something which is there in all these parameters, it is really a tedious task. It's a complex task. So now when you apply the logarithm on both the sides, and if you take the derivative of that log likelihood, you know the likelihood, log likelihood is nothing but applying the log to that likelihood value or to the likelihood function. The interesting thing is that log likelihood and likelihood both peak at the same value for mu and sigma. Okay, so this is an observation, this is an experimental observation. So what it is observed that likelihood and log likelihood both will peak at the same mu value and the sigma value. Okay, even if you calculate the using the log likelihood, it is peaking. The peak value is here, and even if you calculate the maximum value for the log likelihood, the peak value is coming out at the same value. And we are interested only in the peak value, right? Because we are trying to calculate the maximum likelihood. We are not, if you're bothering about any other points, then we cannot go for log likelihood. But we are bothering only for the maximum value because we are interested in only maximum likelihoods. And log likelihood and likelihood are going to peak at the same point, right? So that's the reason you can rely on log likelihood, and it brings the mathematical calculations to very simple. We can solve the mathematical things very easy when you apply the logarithm to it instead of going directly with the likelihood function. if you apply the logarithm to it, you'll just shortly see why the mathematics is very simple. Because when we apply logarithm to different multiplications, they'll become additions, right? Similarly, for the sigma value, the peak is coming at the same value. Okay, so that's the reason there is no harm applying the logarithm, and that applying logarithm will make the calculations very simple. You can just think of taking the derivative with respect to mu for this function. It looks to be very complex. It's okay. If you take the derivative with respect to mu for this function, okay, it is very complex. So um, what you have to do, you have to apply chain rule, right? You have to take rest all of the stuff as y and this as x. So x dy by d mu plus y into dx by nu mu. Could you think applying the derivative with this whole multiplication? It would be very complex. Again, this chain rule will become another chain rule, chain rule, chain rule. It would be very complex. Okay. But when you go back to this logarithmic and expand this, look at this, how simple it actually looks like. Okay. When you apply the log to this particular function, now I'm taking only the first function. Okay. I'm taking only this first equation and applying logarithmic to it. But the interesting thing that you have to notice here is logarithmic of a into b into c into d is nothing but ln of a plus ln of b plus ln of c plus ln of d. You are aware of this, right? Hello?
Yeah. Yeah.
Yeah.
Yeah.
So
Yeah.
now you know the multiplication becomes just an addition. So if you apply
Addition.
derivative for this, it would be very easy. You are just taking the derivative only for this function. So that's why applying logarithmic to this will become very easy. So now let's see what happens when we apply. So now the first A here is, now we are concentrating only on this particular part now. And once we got that result, we apply that to every other thing, because every other thing is same. It's just we need to append them with plus. So what is the first function right now for us? It is 1 by root of 2 root 2 pi sigma square e to the power of minus x1 minus mu whole square by the 2 into sigma square, right? So now how do we expand this? If we apply the logarithmic for that, what actually happens? Let's have a look at that. So it's simple like this. Ln of what we got, 1 by root of 2 pi sigma square e to the power of minus x minus mu whole square by the 2 into sigma square. And now this is multiplication, right? What I can do, ln of 1 by the root of 2 pi sigma square would be one term plus ln of e to the power of minus x minus mu whole square by the 2 into sigma square. This is the base e. Okay. Now what happens? Ln base e to the power of this will become just minus x minus mu whole square by the 2 into sigma square ln of e minus e. So we can bring the power to forward. We can bring this forward, and this ln of e to the base e will become 1. Okay. So this whole function will become this. Okay. Minus x minus mu whole square by the 2 into sigma square. Now let's see what happens with this. Okay. ln of I can make this as 2 pi sigma square whole to the power of minus 1 by 2. So root, I'm converting that to minus 1 by 2. So this comes forward. So this will be minus 1 by 2 ln of 2 pi sigma square. Okay. Again, I'll split this 1 by 2 into ln of 2 pi plus ln of sigma square. Okay. Again, minus 1 by 2 into ln of 2 pi, and this minus 1 by 2 into ln of sigma square. If I bring this 2 forward, and this become ln of sigma, 2 and 2 will get cancelled. And finally, what is remaining here? Minus 1 by 2 ln of 2 pi ln of sigma plus x minus mu whole square by the 2 into sigma square. I mean minus x minus mu whole square by the 2 into sigma square. So these are the three terms that remain, right? Once we expand this, what are the three terms that remained? So this is the first term that remained, this is the second term that remained, and this is the third term that remained. So if you look at this, this is the expansion of this particular equation. And now what I'm going to do here is the same applies for everything else. Now we know this is the expansion for the first time. And now if we keep on expanding this for n terms, what happens? So this will be common for all the n terms. So this becomes n by 2, right? For now we have calculated for only x1. Now we have x1 to xn, and this term will be common for every x. So what we have to do, just multiply this with n. That becomes n by 2 ln of 2 pi. And this is also will be constant for all the terms. So that is minus n into ln of sigma. If you look at this, for x1 it is x1, for x2 it will be x2, for xn it will be xn. So minus x1 minus mu whole square by the 2 into sigma square, so on up to minus xn minus mu whole square by the 2 into sigma square. So this is the expanded form of ln of log likelihood function, okay, where we have n data points. Is this clear? It is
Yeah.
just a mathematical expansion. Now, what's the next step that we need to do? We have to take the derivative of this function with respect to mu and equate that to 0 to get the maximum likelihood value for the mu. Why we are trying to calculate the maximum likelihood? Because that value of mu at which the likelihood is maximum is the optimal value or optimal parameter value or optimal mean value for the distribution that represents the data that we are trying to find out. Okay. Now what I'm going to do is I'm going to take the derivative with respect to the mu. So no mu term here, so it will be 0. No mu term here, so it will be 0. And now if I take the derivative with respect to mu here, it becomes what is the derivative of this function with respect to mu? X1 minus mu whole square by the 2 into sigma square, right? So if I take the derivative with respect to mu, what I'll get? So minus 1 by 2 sigma square is constant. I'll bring this out. Mu by the derivative with respect to mu into x1 minus mu whole square, right? Now I'll bring this 2 forward, minus 2 by 2 into sigma square with respect to mu into, sorry. So we are already taking the derivative with respect to mu, right? So what is that coming up here? So now if you take the derivative of this, it will be just 2 will come forward and this will become x minus mu, and mu minus of mu will be the derivative of this will be minus 1. So minus and minus will become plus, 2 and 2 will cancel. It finally comes down to x1 minus mu by the sigma square. So this is the derivative with respect to mu for this term. Similarly, for every term, it would be the same. For xn, again, 2 comes forward, 2 and 2 will get cancelled. Xn minus mu derivative, xn minus mu into minus 1. So that becomes plus. Okay. So this is the final derivative with respect to mu. And now if you look at this, mu is constant for all the terms, right? X1 minus mu plus x2. Sigma square is the denominator, which is common for everything. So what you do, you take the as the denominator is common for everything, you are going to take that common denominator over here, sigma square. In the numerator, you get x1 minus mu plus x2 minus mu plus so on plus xn minus mu. That is what you have got. And now mu. So there will be n mu's. So that becomes minus n mu. And if you look at this, sum of all the terms, x1 plus x2 plus x3 plus so on xn. When you equate this to 0, what you are getting? So sigma square will go to 0. And finally, mu will become, so this term will come to the right side. So if you just solve this equation, you will get mu is equal to x1 plus x2 plus x3 plus so on xn by the n. Okay. So mean is nothing but the sum of all the points by the number of points. Okay. So that is how you calculate the mean value. That is the maximum likelihood value for that distribution. Okay. We already aware of this, but just to understand in the perspective of how we are saying the mean value is coming down to summation by the number of sum of all the data points by the number of all the data points. It all came down to finding out the maximum likelihood value. Maximum likelihood value is nothing but uh, the value at which the likelihood of the parameters will be maximum. Okay, now you got the mu value, and what is the next thing? The next thing is to find out the sigma value, right? When you want to find out the sigma value, you have to treat mu as constant, and you have to take the derivative with respect to sigma, right? That's what we do here. Again, this is the expanded form of log likelihood. Okay, we already created here, and then now we take the derivative with respect to the sigma. Okay, no sigma term here, so 0. Here we have the sigma term. What is the derivative of log sigma? It is 1 by the sigma, so it becomes minus n by the sigma. And now if you look at this, you have to take the derivative of this with respect to sigma. So if you take the derivative of this with respect to sigma, whole square by the 2 into sigma square, okay, this is all constant. What is the only thing that you have to take the derivative of? But 1 by the sigma square. So you have to take dou by the dou sigma. 1 by the sigma square becomes sigma to the power of minus 2. So the derivative of sigma to the minus 2 is nothing but minus 2 by into sigma of minus 2 minus 1. So this becomes minus 2 by sigma to the power of 3. These are all derivations. So this is a constant term. Minus minus will become plus, and 2 and 2 will get cancelled. That becomes sigma cube. So it all comes down to x1 minus mu whole square by the sigma cube, which is the derivative. Taking the derivative with the sigma will comes down to this one. Okay. Similarly, for all the points, it would be the same. Okay. And then what we're going to do is, this is the equation, right? Now, you equate that to 0. When you equate this to 0, sigma is common here and here. So sigma goes this side and gets equal to 0. And finally, we get remained with minus n by 1 by sigma square into x1 minus mu whole square plus so on xn plus xn minus mu whole square. Okay, n goes that side. Okay, um, so now n is equal to 1 by the sigma square x1 minus mu whole square plus so on plus xn minus mu whole square, and sigma goes that side, n comes this side, and finally that comes down to sigma is equal to x1 minus mu whole square plus so on plus xn minus mu whole square by the n. Okay, so I'm taking this sigma to this here, and then I'm bringing down to the denominator, and sigma square, when square is coming to this side, it is becoming root. And finally, we know the formula for calculating the standard deviation. It is nothing but sigma I is equal to 1 to n xi minus mu whole square by the n root of, right? This is sigma squares. And when you're trying to find out the standard deviation, this is the formula for variance, right? Sigma is equal to 1 to n xi minus mu whole square by the n, which is represented by sigma square. When you want the standard deviation, it is just the square root of the variance. Okay, so you're already aware of this particular formula. Now, when you got mu and sigma, you can just draw the graph for that particular distribution. Okay, this is how you calculate the mu and sigma values. That exactly represents the um, distribution. Okay, mean is nothing but the sum of data points by the number of data points. Standard deviation is nothing but square root of x minus mu whole square. Square root of sigma is equal to 1 to n xi minus mu whole square by the n. Okay, that is what maximum likelihood is. So the main intention here is just to show you what is likelihood, how do we calculate the likelihood, and how do we calculate the maximum likelihoods, and what do we mean, what is the intention behind calculating the maximum likelihoods. Is everything clear so far?
Yes.
Yeah.
Okay. Now going back to the next thing. Now let's understand what is this odds and log of odds. Okay. These concepts will be used in logistic regression. So you need to be aware of these things. Okay. So it is easy to understand when we say odds. Okay. Let's just say when we say odds, odds is nothing but the odds are the ratio of something happening by something not happen. Okay, that is what actually odds is. If you take an example, just the odds in favor of my team winning the game. Okay, odds in favor of my team winning the game. And that means what is the favor? Odds of favor means how, what is it's not probability. Probability is different. Probability is the probability of winning by total trials, right? That is what probability is. But odds is probable ratio of something happening to the something not happening. Probability is something happening to the total number of events. That is the difference. Okay. So if you look at this, odds are the ratio of something happening to the something not happening. The odds in favor of my team winning. So out of 5 games, my team winning chances is 1 game and my team losing chances is 4 games. That means win is happening to win not happening, which is mean by fail, which means that the team is losing. Okay, winning by the losing, uh, happening to not happening. That is what actually odds means. Okay, what is probability? Probability is nothing but ratio of something happening to everything that could happen. That means if you're playing 8 games, okay, if you're playing 8 games, out of that, if you're able to win only 5 games, the probability would be 5 by 8, but log of odds would be 5 by 3, because out of 8 games, what the winning is happening in 5 games, winning is not happening in 3 games. So this is called as odds. This is called as probability. Okay. Now let's look at this. Now we want to link the odds with probabilities. Okay. We want to map odds with probabilities. That's what we are going to do now. Okay. Now calculating odds from probabilities. This is, let's suppose if you're playing 8 games, out of 8 games, you're winning 5 games. Okay. And you're losing 3 games. If you look at this particular thing, this is the probability of winning, which is 5 by 8. What is the probability of losing? It is 3 by 8, right? Um, Probability of winning, if you take the probability of winning as P, probability of losing will be 1 by the P, right? Is that correct? When probability
Yes.
is P, probability of losing will be 1 minus P. Okay. And if you divide these two things, the same 8 games we are playing here as well. Out of 8 games, we won 5 games, lost 3 games. So now if you divide these two, we are getting the same thing, 5 by 3. Okay. If you take the probability of winning by probability of losing, we are getting probability of logs. I mean, we are getting the odds ratio. Sorry, we are getting the odds, right? If you look at this, the odds value here is 5 by 3, which is nothing but probability of winning by probability of losing. That means when you divide these two things, we are getting 5 by 3. So we can say odds is nothing but probability of winning by probability of losing. Okay, just this, if you take this example, out of 8 different games, if you win 5 games and losing 3 games, or log of odds is nothing but 5 by 3, something happening by something not happening. Probability of winning is 5 by 8 and probability of losing is 3 by 8. And if you divide these two, we're getting the log of odds. Probability of winning is nothing but, when you consider probability of winning as P, probability of losing is 1 minus P. So odds is nothing but probability by 1 minus probability. Okay. The ratio of probability of winning to the probability of losing. Probability of losing is nothing but 1 minus probability of building. 1 minus probability of winning. So odds can be written as P minus 1 minus P. If we apply logarithmic to this, we call this as log of odds. Okay. Okay. So that is what odds and probability means, and this is how we relate odds with the probabilities. Okay, and this function is called as logit function. Log of probability, log of the ratio of the probabilities is called as logit function, and forms the basis. And this will be used in logistic regression, basically odds and log of odds, log odds ratio. All this will be used in logistic regression, and maybe we may not discuss that today, but we will eventually go to logistic regression, and when we will see these concepts coming there. So odds is nothing but something happening by something not happening. Probability is nothing but something happening by everything that could happen, or total number of events. And if you want to link up odds with probabilities, it is nothing but odds is equal to probabilities by I mean probability of something happening by uh, probability of something not happening. That is p by 1 minus p. And if you apply a logarithmic to that, it becomes log of odds. Okay. Log of odds is nothing but logit function. All right. So this is all about odds and log of odds. Okay. Now we will go back to R squared. So far we have discussed the difference between probability and likelihood, calculating the likelihood, and we understood what is maximum likelihood, calculating the maximum likelihood for a normal distribution. And we also have seen different kinds of distributions, just how different distributions looks like. We have seen about normal distribution, exponential distribution, and gamma distribution. Okay. Depending on the data that you have, you can fit any distribution that you want to. To find out any of the distribution parameters, again, for any distribution, you just have to calculate the maximum likelihoods, and then take the value where take the parameter value, or set the parameter value where the likelihood is maximum. Okay. Yeah, that's all the basics. Now we are going slowly to linear regression, understanding the basic concepts of linear regression, and then we will see what is linear regression, and how does that. I hope you all know what is a regression, right? Which kind of models are called as regressions? We talked about this when we talked about like recently we have gone through that uh, gradient boost, right? Gradient boost for regression, gradient boost for classification. We have talked about those two things. When you say regression, you are trying to predict a continuous value. When you say classification, you do classify whether that belongs to a spam email or not a spam email, dog or not dog. Okay. If a multi-class classifier, you say whether that is got dog, cat, or any other animal. Okay. Whereas in regression, the main idea behind regression is to find out a continuous value. The output would be a continuous value. It is not just a binary thing, 1 or 0 or yes or no. It would be a continuous value. So when you say continuous value, it can come from any some set of ranges. So that when I say linear regression, the output that you can expect is an integer value. Okay. So we will just we'll take a break for 10 minutes, and then we will see the basics of linear regression, and then we will go from there, understanding and completing the linear regression stuff. Yeah, let's catch up in 10 minutes. I'll be back in 10 minutes. So now we will talk about R squared. R squared actually means is square of residuals. Okay. Uh, R stands for residual. What does residual actually means is that it's the difference between the actual value and the predicted value. Okay. So that's the difference between actual value and the predicted value, right? So that is what residual actually means is. Okay. So if you look at this diagram, so we are trying to find out the mouse weight using the mouse size. Okay. If you look at these data points, these are different mouses available, right? These are different mouses. So this mouse is the smallest mouse, and the weight is this. The weight of this mouse is this. Similarly, um, if you look at this mouse size is somewhere between small and large, and the mouse weight is something like this. Okay. And if you take this particular mouse, this mouse is the largest, and the weight of this mouse is this. Okay. So these, if you look at this data point, this is the actual weight of this mouse. Okay. This is the actual weight of this mouse. But what is the predicted? Okay, we created a model. We tried to fit a line to this data. If you look at this data, this is linearly dependent, right? So as the mouse size is increasing, the weight is also increasing. So there is a linear relationship between the mouse weight and the size. And now we try to fit a line. Okay, we try to fit a line to these data points. Okay, and now if someone gave me a particular weight, if someone gave me the weight here, and what is my predicted value, I'll just project, I'll see where it touches this particular line, and the relevant value of the weight would be the weight of this mouse. That is the predicted. Okay, if you look at this particular data point, this is the actual weight. Okay, this is the actual weight. But what is the predicted weight for us? The predicted weight is this weight, like we project onto this. So this is the size of this mouse, and to this size we predicted, this blue line is a predicted. So this is the predicted weight of the mouse. So this difference is called as the residual. Okay, so we are squaring, r square is nothing but the sum of the squared residuals. Residual is nothing but the difference between the actual weight, actual value, and the predicted value. Okay, so we will again see more examples related to this, but that is what R squared means. It is also known as the coefficient of determination, is a statistical matrix that measures the proportion of variance in the dependent variable y that is explained by the independent variable in the regression model. Let's understand this. It measures the proportion of variation in the dependent variable. Okay, that is explained by the independent variable in a regression model. What is the dependent variable and what is the independent variable here? Dependent variable is mouse weight. If you look at this diagram, mouse weight, this is y-axis, this is x-axis, right? This line can be represented by y is equal to mx plus c. So y is dependent on x. Based on the value of x, y value will be decided. So y is known as the dependent variable, x is known as the independent variable. Okay, so mouse size is independent. So we are trying to predict the mouse weight based on the mouse size. Okay, so now this says R square says it's a statistical matrix that measures the proportion of variance in the dependent variable. Variance in the dependent variable. Variance is nothing but the deviation from the mean. The variance in the dependent variable that is explained by the independent variable x. Variance in dependent variable that is explained by the independent variable is r square. Okay, so now let's understand this with different examples. Okay, now coming back here. Now look at this particular line here. So how to explain this? Now what you have to calculate, variance, that variance in the dependent variable that is explained by the independent variable. Okay, now what we have to calculate, variance in the dependent variable. So variance in the dependent variable that is explained by the independent variable. Okay, so how do we say how much variance in this is explained by this is nothing but you just have to subtract this by variance of y, right? That is what actually variance of y explained by x means. Okay, how to make this to you? So all we bother is variance in y, variance in dependent variable that is explained by the independent variable x. What is the variance in y that is explained by variance in x? That's what we are bothered about, right? Let's take two buildings. Okay, let's see this example. If I have two buildings, okay, the height of this is 100 meters and the height of this is 50 meters. Okay, what is the height of building A explained by building B? Okay, that means height of building A that is explained by height of building B. So half of the height of building A is explained by building B, right? So height of building A is 100 minus height of building B is 50 by 100. That is 50 by 100, which is 1 by 2, right? So that means similar way, okay? If you take this same example here, the same applies here as well. So one building height is 100 feet and the other building height is 50 feet. Now we want to understand how much weight, how much height of the first building is explained by the second building. Exactly half of the first building's height is explained by the second building, right? So if you look 100 and 50, okay, what you have done, so you are subtracting this value from this value, because you want to know how much is explained compared to this. So we are dividing that by 100. So finally, where we are getting there here. So now the similar applies. This is variance of y, this is variance of x. We want to know how much variance of by the how much variance of independent dependent variable explained with independent variable is nothing but v of y minus v of x by v of y. So that is what actually r square means. Okay, r square means the variance in the independent variable that is explained by the dependent variable. And now when I say variance of mean, what does this variance of mean is? Okay, that's what we have to understand. So let's substitute some values before going there. Let's substitute some values. Okay, let's suppose we understood this is the formula because we are trying to understand what variance in the mean that is explained by the variance in the line. So variance along the dependent variable, that means, so these are different points given to us, right? So these are all the points given to us. And now what is the dependent variable? Dependent variable is mouse weight. Okay, so dependent variable is mouse weight. And now you have to calculate the variance. What we need mu, right? We need mean of that variable. So we need mu, and then to calculate the variance, what is the formula? X minus mu whole square by the n, right? That is how you calculate the variance. Is that right? This is the formula of the variance. I is equal to 1 to n x minus mu whole square by the n. So now to calculate the variance along the dependent variable, what you have to find? You have to find out the mean of all these data points. Let's suppose if you look at this particular mouse, the weight of this mouse is this value. The weight of this mouse is this value. The weight of this mouse is this value. The weight of this is this. This is this. This is this, and this is this. Now we know these are all the data. These are all the weights of different mouses. To know the mean of these points, what you have to do? You have to take the sum of all these values by number of these points, right? Number of mice that are there. And then once you know the mean, so the mean will fall somewhere here. So now if you extend this line, this is the mean line. So this is the mean line. And then what you have to do? You have to subtract this mean from every point. Okay, you have to subtract the mean from every point and then you have to square it. Okay, that's how you calculate the variance by n. Okay, so that is how you calculate the variance along the mean. And now variance along the line. How do you calculate the variance along the line? Variance along the line is nothing but, again, what is the mean value? This is the line that we have, right? We are trying to calculate the variance along this line. And then what do? You project all these points onto this line and then take the mean value and then take the x minus mu. So you subtract the mean from every point and then square it. That is how you calculate the variance along the line. Okay, so that once you calculate the variance along the mean and variance along the line, you can calculate the value of r square. R square specifies how much variance in the dependent variable will be explained by the independent variable. Let's suppose if you take the value of mean as 32 and variance along the line as 6, and if you calculate the value of r square, that comes down to 32 minus 6 by 32, which is 81%. That means 81% of the variance in dependent variable is explained by the independent variable. Okay, there is 81% less variation around the line than the mean. Okay, So that much of variance is reduced, okay, in the new line. Or else you can say the size and weight relationship accounts for 81% of the variation. So this actually means is that mouse size explained or covered 80% of the variation in the mouse weight. That means this variation can be explained by the mouse size. Okay, let's take some edge cases and then you will understand how does this actually looks like. So this is the best fitting line, right? This is the best fitting line for the data. You are seeing this as the best fit to the data. So this is all the data points, and this line most probably covered 3 points. 3 points are on the line and other points are very close to that line, the predicted line. So that's the reason you got the R square as 81 percentage more value. When the line didn't fit the data pretty well, you will get the low R square values. If you look at this particular data set, this is the mean line. So this is the variance along the around the mean, and this is the predicted line that you have done. So if you look at this doesn't represent this data at all, right? This is not a good representation of the data, the blue line. So the variance along that line is also high. From the mean of the data point, the points spread widely. Okay, in that case the variance will be more. And when you calculate the R square substituting these values, you're getting you got 6%. That means only 6% of variance, uh, only 6% of variance along the mouse weight is explained by the so the y variable is time spent sniffing a rock. So there is no relationship between mouse weight and the time spent sniffing a rock. So there won't be any relation explained. I mean, uh, the sniff and weight relationship accounts for only 6% of the variation. So there won't be much variation explained by the sniffing a rock activity. Mouse size and mouse weight are interrelated. That's the reason when the mouse size is high, mouse weight will be high. Okay, as they are interrelated, most of the variance in the weight, weight is explained by the size. Whereas in this case, they are not related to each other, and there is no relation between these two variables. So there will be very less variation that explained by the uh, time spent sniffing a rock to the mouse weight. So there is no relationship between them. So when R square is equal to when R square value is less, that means there is no relationship between those two variables. Okay. When R square is equal to 0, let's take an example. If R square is equal to 0.9, that means 90% of the variance in the dependent variable is explained by the independent variable. There is a strong relation between both of them. But if the R square is very, very less, then the relationship between the two variables would be very, very less. Okay. That means only relationship between the two variables explains only 1% of variation in the data. So something else must explain 99%. So that is, as these two are not related, there should be some other variable that explains that. Okay. To keep it short, R square is nothing but when R square is high, we can say that there is a high relationship between those two variables. Okay, that means variance in the dependent variable is explained by the independent variable. Okay, if you look at this, R square always will be between 0 and 1. If R square is equal to 1, the model explains 100% of variation in the dependent variable. Okay, that means 100% of variation in the dependent variable means, I think I should show you an example here. Perfectly fit. So 100% of variation explained by the dependent variable, in the sense, if you take this as a line and this is weight, and if you take this as a size, and if you consider this particular, if the points looks like this, okay, if the points look like this, here R is equal to 1. That means variation around the mean would be very high, and variation along the line will be 0. If you look at this, let's suppose if you take all these points onto this axis, and if you calculate the mean of variation around the mean, if this is the mean and this is the variance, let's say variance around the mean is equal to some 20, but variance along the line is equal to 0, right? because every point lied on this line. Okay, so if you want to calculate the variance, it would be very less, right? This is the line and these are all the data points, and every data point lied on this particular line. Okay, so the variation along the line will be equal to 0. So variation along the mean minus 0 by variance along the mean, which will be equal to 1. So r square is equal to 1. That means these two are these two variables are highly related. That means weight is equal to some slope into some slope, let's say 2 into size of the mouse. Okay, so if r square is equal to 0 means the model explains none of the variance. So the model is not explaining any variance in the data. Okay, and if r square is less than 0, less than indicates the model perform worse than simply uh, r square less than 0 means model performs worse than using the mean. Using the mean in the sense when you project all the data points onto the mean and calculating the variance of the when will r square will be less than 1? R square will be less than 1 when variance along the when this value is greater than this value. That means line is performing worse than the mean. Okay, in that case only r square will be less than 1. This value has to be greater than this value, then only r square will be less than 1. That means this indicates the model performs worse than simply using the mean. So simply using the mean means uh, by simply using the mean, if you're simply using this, this line is performing worse than the mean. That is the case when r square will be less than 1. Okay, so what is this r square? In simple terms, if you have to understand this, so let me show you this. Let's understand more about this r square before going further. I think SS mean is coming down here. Okay, so when I say variance along the mean, okay, calculating the variance, mean, and all that stuff. But when let me talk about this r square less than 1. This says the model or the line, the line that you have fitted is acting worse than the mean. Okay, then only when this value is greater than variance along the mean, then only you will get r square less than 1. I mean r square less than 0, right? Negative values. R square less than 0 is nothing but negative values. When do you get negative values for r square? When variance along the line is greater than variance along the mean. What do you mean by variance along the line is greater than variance along the mean means? How do you see the mean as? So whatever mouse that you're predicting the mouse weight, right? If you're predicting the mouse weight, let's suppose, yeah, I would have taken numerical examples. Let's say the mouse weight is 20 kgs. Okay, this is the mean weight that you're predicting for every mouse. So now, when you come up with only one, which is mean variance along the mean, let's come up with a value called as mean is equal to 20 for these data points. So the mean is coming as 20. So wherever the mouse comes, whether it is a large mouse, small mouse, medium mouse, or very large mouse, your model says the weight of the mouse is equal to 20. Okay, because you're not fitting up any line, you're just saying, picking up the mean value, which is the best representation of all the data points, right? Mean is nothing but a central tendency, the best representation of all the data points. Okay, now if you look at this, the mean is the one. This is the worst case, right? So mean is the worst case thing. If there is something which is behaving much worse than mean, and in that case only we will get r square less than 0, the negative values. But in the real world, it doesn't really happens. So every time you'll get, uh, so the range of R will always be in between 0 and 1. Okay. So that is what R square means. R square is nothing but how much of the variance in the dependent variable is explained by the independent variable. Okay. Um, so that we can come up by subtracting the variance of the line minus, I mean, variance of the mean minus variance of the line by variance along the mean. Okay. And now, why we are studying all this stuff, R square and all these things is the main idea behind linear regression is given some data points, you want to come up with an optimal line that exactly fits the data. So if you look at this, these are different data points given to us. And these are different lines that are possible that represents these data points, right? These are the different values that represents these data points. But which is the best fit for all these points? Line 1, line 2, line 3. Which is the best fit? So to predict that, we need to do some sort of you know, uh, some sort of parameter should be there to understand which line better fits these data points. Okay. Do you understand what does fitting a line to the data points actually means is? Hello. Think
Yeah.
I Yeah, I let me just explain you, which is very important. I think I would have kept a numerical example, but I haven't kept that. So let me just draw something, so you will understand what does fitting a line to the model. I think we already discussed these things in the when we discussed earlier, but let me just explain you. Let's suppose I have got these values, okay? So let's suppose scored number of runs scored by a player, okay? Number of runs scored by a player. Let's suppose I say 10, 20, 30, 40, something like this, 50, 60. So these are matches. Okay. So this is match 1, match 2, match 3, match 4, match 5, match 6, match 7, something of the sort. Now we got some points. The first match is scored 10. In the second match he scored 25. In the third match he scored somewhere around 17. This is 10, 25, 17. And in the fourth match he scored somewhere around let's suppose 20. Okay. Now I these are the real data that I do have. Now when I say I'm fitting a line to this data means, now I use some machine learning model and I came up with some prediction. So I fit a line to these data points. What does fitting a line to the data points means? Now this is what the model predicted. Okay. So this is predicted and these are actuals. Okay. This is represented by Y and this is represented by Y hat. And now what does predicted says for match 1? The predicted is when you expand this match 1 onto this particular line, this point on this y-axis is the number of lines. So if you look at this, this is somewhere between 10 and 20 and it is predicted as 15. So for in the first match he scored 10, but the model predicted them as 15. So this is actual and this is predicted. And if you look at match 2, the prediction is 20, but the actual is 25. So 25, the prediction is 20. Okay. And if you look at match 3, the prediction is 17, but the actual is 17. But what is predicted? Predicted is somewhere around 27. Okay. So that is actual and prediction. So if this model is performing very well, in you can predict what he can score in sixth match. It will be somewhere around 50. What he can score in seventh match, somewhere around 55. Okay. Now it all depends on how well you fit this data to this data points, right? So you see there is a lot of variation. Okay. If you can slightly shift this line like this, then the difference is reduced very well, right? Just a second. Okay. So hello.
Yeah. Yeah.
Screen కనిపిస్తుందా?
Huh.
Okay. So if you look at these lines, if you slightly shift this, it may come little closer. Like if you choose another line, the predicted can be somewhere around 9, 24, and if it is 18, if the predictors are coming like this, so this line is performing better than this line. We can say this fit is performing better than this fit. Okay, that is what actually fitting a line actually means is, and like I said, this can have predicted values much closer to the actual values when compared to these two lines. And how can we decide which is the best fit? And that can be measured using something called as residuals. As I already told you, residual is nothing but the difference between the actual value and the predicted value. Okay. So now you need to measure the fits. The measure of fit is known as the residuals. You need to calculate the residuals for this line, and this line, and whichever is lesser, we will we will consider that line as the best fit for the data. Okay. So the distance from the line to the data point is called as residual. What is the line? The line is the predicted line. Okay. The fit that we have made for the data points. So the worst case fit is the mean of all the data points. Okay. So the worst case is take the mean of all the data points and use that as the fit for all the data points. So whatever the weight of the mouse or whatever the size of the mouse, we always say the weight of the mouse as the mean of the weight. So that is the worst case. Okay. So this is the mean, and this is the worst case prediction of the data. The best case is like fitting a line like this, as there is a linear relationship, and this is the mean prediction. Okay, which is the central tendency of all the data points. But there could be a lot of the residual difference. But let's see, now we consider the mean as the fit for these data points, and then we calculated the residuals. The residuals is nothing but the difference between the line and the data point, right? We always take the squares because we should this will be negative value, right? So y1 is below the mean, so this will be negative and this will be positive. So we don't want to cancel these each other, right? So that's the reason we square them as they are distances. So what we have done, we have taken the mean and we subtracted that with this value and squared that. So that is the residual. Similarly, we calculate the residual for every data point and square that and summate that, and you will get some value. This is the sum of squared residuals. This is called as sum of the squared residual is the distance from the line to the data point. And here what you have done, you have squared the residual and then have taken the sum. So it is called the sum of the squared residuals because the residuals are the difference between the real data and the line, and we are summing up the square of these values. So that is the reason we are taking this is called as sum of squared residuals. Similarly, we calculated the sum of squared residuals for the mean, and we also calculate the sum of squared residuals for every other line. And whichever line has the smallest sum of squared residuals, we call that as the best fitting line to the data. Okay. Now I just have, this is the mean, right? Now I rotated the line a bit. Okay. I rotated the line, and then what I have got the sum of squared residuals as 14.05 in this case. Here the sum of squared residuals is 24.62, and here it is 14.5. And if you look at this, 20, what we have got earlier, 24.62 for mean. For mean line, we got 24.62. And for this line, we got 14.5, 14.05. So sum of squared residuals for this line is less than this line. So this is considered as the best fitting line when compared to this mean line. And if you still rotate this, okay, if you rotate the line a lot, okay, earlier it is like this, now we rotate it a bit, and if we still rotated this to a more vertical, to look like a more vertical, and if you calculate the sum of squared residuals here, it is 31.71. Okay, and we got somewhere around 31.71. Okay, if you look at this, this is the horizontal mean line, and this almost looking like a vertical, and this is slightly in between these two rotations. Okay, what you have to understand is that there is a sweet spot between horizontal and two vertical. Okay, there is a sweet spot between horizontal and two vertical. This is the sweet spot. Okay, that would be the optimal fit for the data. Okay, the line has to, if you consider the horizontal, that is the mean, and if you go for two vertical, there also the sum of squared residuals is getting too high than the mean, but in between these two we are getting some value of sum of squared residuals for some rotation between two horizontal and two vertical. That is the sweet spot that is considered as an optimal fit for the data. Now, how do you find that sweet spot is what you have to understand now. It is now you came to know that sum of squared residuals has to be less. For whichever line the sum of squared residuals is less, that is considered as the optimal fit. Now you have to find out what is that line. How to calculate that optimal sum of squared residuals. Okay, that's what you will understand now. Now, any line can be represented by, this line can be represented by y is equal to ax plus b, that you know, and this line can be represented by y is equal to ax plus b, right? So, for example, let's take another point. If example this is point y1, okay, this is actual value y1, okay, and now what is the predicted value for this? Predicted value for this is this. So if this is x1, okay, let's suppose this is x2, this is x3, and now what will be the predicted value? Predicted value is, if this line is y is equal to ax plus b, to get the predicted value you just have to substitute x in this line, right? X here, so you will get the predicted value. So predicted value is equal to a into x1 plus b. What is the actual value? Minus y1. So this is residual. We need sum of squared residuals. So for every point you take the predicted value, you take the actual value, subtract them and square them. Similarly, you do that for all the data points. Okay. Now this is how this is the loss function for us now, sum of squared residuals. Now you have to take the derivative of this, equate that to 0, and then find out the required value. That's all we do in any case. Since we want the line that gives us the smallest sum of squared residuals, this method is finding values for a and b are called as least squares. Okay, this method of finding the values of a and b are called as least squares, because we are trying to find out the smallest sum of squares. That is nothing but, smallest sum of squares is nothing but least squares. So this method is called as least squares method. Okay, what you do, so this is like the similar thing as I mentioned to you earlier. This is the horizontal line, and this is the sum of squared residuals. You had done a slight rotation, and this is sum of squared residuals. Some more rotation, this is sum of squared residuals. Some more vertical rotation, this is, as at some point the sum of squared residuals again started increasing, right? So this is the sweet spot, and this rotation is the one with with the least squares. So it is the one that fits the data. Okay, and you look at this. Now what do you have? You have ax plus b, right? You need to find out both of them. You need to find out the slope and also the intercept. Then only you will get that particular line, right? So this is for one. This is when you're increasing the slope of that line, you're changing the slope, but intercept is made constant. When you keep on changing the intercept as well, this is for one intercept value, and this graph is for another intercept value, and this graph for another intercept value. Let's take some values here. Let's suppose intercept value is 1, 2, 3, 4. When intercept is set to 1, and when you're changing the slopes, these are the sum of squared residuals. When intercept is set to 2 and we are changing the value, when you're changing the slopes, these are sum of squared residuals. Similarly, you do that for n number of intercepts. by changing the slopes, and finally out of all these graphs you try to find out the minimal point. Okay, taking the derivative of both the slope and intercept tells us where the optimal values are the best fit. Okay, so you keep changing intercepts, you keep changing slopes for every intercept, and then you will find out the minimum value of all of them, which will gives the optimal uh, which will give the optimal fit for the data. But no one ever solves these kind of things in on a paper by hand. These are all done by the statistical softwares. Okay, this is possible only by the computers, so computers will do that. But just for theory knowledge, we have to understand how does this slope and intercept will be calculated to for the best fit line. Okay, and now again coming back to the old thing, earlier what we have done, r square, we want r square to be more, right? uh, so we want more variance to be explained of the dependent variables should be explained by the independent variable. Now let's slightly change that to a different formula. So what do you know by variance around the mean? Variance around the mean is nothing but data minus mean by mean whole square by the end. This is the variance formula. We all know that we do that for every data point. Now we can write sum of squared means. Sum of squared means is nothing but just now you have seen the predicted value minus the actual value, right? The predicted value minus actual value. So data is the predicted value, and when for the mean line, predicted is mean and the actual is data. Okay, because when you set a mean line, this mean line doesn't is nothing but you're making the prediction of every sample as the mean. Okay, that is what variance of mean is. So you can say variance of mean can be written as the numerator is sum of squares of the mean by n. Similarly, for the fit, this is the optimal line that you have fit to the data. For the fit to the data, it can be written as sum of squares of the fit, because sum of squares of fit is nothing but data minus line. This is the line by the whole square by the n. So whatever value that comes on this line is the predicted. This is the actual. So variance of the fit can be written as SS of fit by the n. Now finally, R square can be written as SS of mean minus SS of fit by SS of mean, because R square is nothing but variance along the mean minus variance along the fit by variance along the mean, right? So variance along the mean now is now replaced by sum of squares along the mean by n, minus variance along the fit is nothing but sum of squares along the fit by n by sum of squares along the mean by n. So n will cancel. So finally you'll get sum of squares along the mean minus sum of squares along the fit by sum of squares along the mean. So that is what r square actually means is now. So that's the new derivation for r square. So no more we rely on variances, because the data points are same for everything. So if you look at this, this is the less variation. So if you look at this, less variation around the line that we fit by the least squares, which is um, so there is this weight mouse relationship explains some variance in this data, right? So the mouse variation, this data is explained by the mouse weight. Okay, here we are deriving mouse size from the mouse weight. Okay, that means the variance in the mouse size is explained by the mouse weight, because they are interrelated to each other and r square value is high. Okay, that is what actually it means is, so variation in the mouse size, that means some mouse are here, some mouse are here. Okay, this variation is explained by the mouse weight. How it is explained? By fitting an optimal line to it. So when the weight of the mouse is high, the size is described as high. When the weight of the mouse is low, size is also low. So that variation is explained by this variation in the mouse weight. Not 100% is, but to some extent it is explained. That is determined by the r square value. Okay. Again, some more examples for you to understand this R square a little better. So now if you look at this, variance along the mean for this points is 11.1. Okay. As I told you, R square is equal to 0 here. So none of the variance um, in the size is explained by the weight. Okay, so none of the variance in the size is explained by the weight. That's the reason R square is equal to 0. If you look at this is the variance of the mouse size, right? So we calculated the variance and it comes down to 0.1. And similarly, if you look at this, there is no relationship between the size and weight here. Okay, heavy, I mean, heavier mouses are small and also large. So when you calculate the variance for these data points from the mean of these data points, again, you got 11.1. So when you calculate the R square, it comes down to 0. That means none of the variance in the size is explained by the weight. In this case, mouse weight doesn't explain any of the variation around the mean. Okay, that is for single variables. R square for multi variable models. So far we have calculated R square for only two variables, right? There are only two axes. But if we have multiple axes, how do we do that? We do that by fitting a line to this data. So how does if it is two dimensional, the line looks like this, right? Y is equal to mx plus c. If there are more number of variables, the line can comes down to m1 x1 plus m2 x2 plus so on mn xn, depending on the number of dimensions that we do have. So this is how that looks like. So now when you have two dimensions, so that they look like x is mouse weight, z is tail length. So your equation keeps on extending. So it would become plane instead of line. This would become plane. Okay. If the tail length z-axis is useless and doesn't make SS fit smaller, then least squares will ignore it by making the parameter to 0. Okay. If you look at this, if the body length of this mice is not explained by the tail length. If there is no relationship between the body length and the tail length, and none of the variance in the body length is explained by the tail length, then that will be multiplied by the 0. That parameter will be ignored by making that by making that parameter equal to 0. So we are multiplying that parameter with 0. So you are not considering that. So even though we have n number of parameters, your line that you're fitting will not be impacted because that variable will be set to equal, will be multiplied by 0. So that will become void. Okay. This is all about multivariable model for R square calculation for multivariable model where, you fit a plane instead of a line for these kind of models. Okay. Um, I think we have gone with so many examples, but R square is simply means like we are trying to see if there is any relationship between the dependent variable and the independent variable, because we are trying to represent the dependent variable using the independent variable. So R square is all about, if you look at this, you have seen a lot of jumblings here and there. Maybe I need to rearrange these slides later. Uh, R square is all about this thing. So what we are trying to find out here, we are trying to come up with a line to fit the data, right? You have the data something like this in a two-dimensional space. And now you are trying to come up with a line that fits the data. Okay. If you consider this as y and this as x, you want to represent y with x. Okay. And you want to represent this y with respect, this line is nothing but y is equal to mx plus c, right? That means using the values of x, y is predicted. Okay, for different values of x, you are predicting the value of y. If this can happen only if there is a relationship between y and x. Okay, something like if mouse weight is increasing, size will increase. If there is no such relationship between this y and x, then r square will be equal to 0. Why r square will be equal to 0? Because r square tells us how much variance or what is variance, the deviation or the data distribution. how the data distribution along y is explained by the x. If you look at this case, y cannot be predicted with by using the value of x. If you take this x value, for the same x you have different y values. So in this case you cannot predict y using x. You cannot come up with one single line that represents that helps us predict y from the x, right? You cannot come up with any lines. Okay, so in this case r square is equal to 0. Okay, so all you're doing with r square is you're trying to come up with a fit line that fits the data. That's all. If how can you when you can fit the data, if there is a relationship between those two variables, right? If there is relationship between y and x, you can come up with a line. If there is no relationship between y and x, you cannot come up with any line, right? You cannot come up with a straight line. Linear regression is all about linear. There should be a linear relationship between the variables, then only you can come up with a linear line. Okay, linear regression is nothing but fitting a linear line to the data, and fitting a line to the data is possible only when if there is a relationship between these two dimensions. If there is no relationship, then you cannot fit a line, then linear regression is not possible. When linear regression is not possible, r square will be equal to 0, and r square is equal to 1 when there is a perfect fit. That perfect fit means if all the points lies on this line, you're exactly predicting the values. That means predicted value is same as the actual value. If the mouse size is 20, you're predicting that as 20. If mouse size is 30, the prediction you're predicting that as 30. Okay. In that case, r square, what is the r square comes down to? R square is nothing but variance along the mean minus variance along the fit by 0, right? So in that case, variance along the line will be equal to variance along the fit. Sorry. Um, how can I come with this? You understood this case, right? Why are we consider r square? If there is no relationship, r square will be equal to 0 because mean will be variance along the mean will be same as the variance along the fit here, because this is the best fitting line in both the cases. So then r square is coming down to 0. Okay, that is all about r square. R square is just a measure of how is the is the parameters. It's nothing but it explains how much variance along the y-axis or the independent variable is explained by the independent variable. Okay. Now coming back to the linear regression. In linear regression, what all we are trying to do? We are just trying to do, we are just trying to fit a line. Y is equal to wx plus b. Okay. When you have only two dimensions. If you have n number of dimensions, then y will be w1 x1 weight along the first dimension plus weight along the second dimension plus so on plus b, right? So if it is a multi-dimensional or multi-dimensional linear regression, multinomial linear regression, then the equation looks like this. Okay, so this is all about linear regression. Linear regression is all about fitting a line to the data. Linear regression is a supervised learning algorithm. You know what is a supervised machine learning algorithm? Used to model the relationship between dependent variable and one or more independent variables. The goal is to find a best fitting line in case of two-dimensional data, and if it is in higher dimensions, it is called as hyperplane, that minimizes the errors between the predicted values and the actual values. So the whole agenda of linear regression is to minimize the difference between the actual values and the predicted values. Okay, so now consider this. Let's suppose you are coming up with something like this. Like you have n-dimensional data. So you have n-dimensional data. So these are all x-axis. These are all different points, and this is x1, x2, x3, so on xn, and this is the predictions. These are the actual predictions y. Okay. Now you need to map all these variables with y. Okay. How do you do that? Now let's understand what are the dimensions of these data sets. Okay. Okay, if you look at this, this is what the data is now, right? So these are different the features or dimensions that are given to us. So this is the predicted values. So what is the dimension of predicted? Y is one vector, right? So this is the predictor for point 1, point 2, and these are the predictions for n points. So y is n by 1 vector, right? So y is n by 1 vector. So what about w? W is nothing but it's a slope, right? So if you consider one-dimensional data, it is y is equal to mx plus c, right? So this is W1. When you have more dimensions, this looks to be W1 x1 plus W2 x2. So this is one dimension, this is second dimension. So if you want to come up with an hyperplane, what is the equation of that hyperplane? So that comes down to W1 x1 plus W2 x2 plus so on wn xn, right? So if you look at this, for every dimension you're getting one w, right? For every dimension you're getting one w, one weight. Similarly for d dimensions, I mean, for let's suppose this is dxt, these are endpoints and these are d dimensions. So for d dimensions you are getting d weights. So w is nothing but w weight vector is nothing but d by 1 weight vector. And what about this matrix? This is n by d, right? This is n by d feature matrix. These are n points and d dimensions. Okay. This is all without bias. So every straight line will have a bias. A bias is nothing but where it intersects with the x-axis. I mean, with the y-axis. That is what intercept is, right? Now, if I want to convert this to vectors, okay, if I'm writing x as like this, x1, x2, x3, so on, 1. Why I'm writing 1 here? You already understood this. So this is to eliminate or incorporate that b into that b into the weight vector. So instead of writing y is equal to w1 x1 plus w2 x2 so on plus wn xn plus b, I am extending b into 1, vector 1. B can be written as b into 1, right? 1 can be a vector. So if I separate this, all the weight vectors like this, weight vectors now will be w1, w2, so on, wn, and after wn, I am also incorporating b. This multiplied with x1, x2, x3, so on, xn, and the last vector is 1. Okay, so if I multiply these two, it becomes w1 x1, w2 x2, w3 x3, so on w1 xn plus b into 1. So that intercept will be this b. So now x can be written as x1, x2, x3, so on xn, and last one vector. This one vector we are incorporating because we don't want to calculate b separately. We already discussed these concepts earlier. So why we are adding b into this vector w? You don't want to do multiple calculations for coming up with b again. So if you want to know the b, once w vector is calculated, you can just take the last value of the w as the b value. Okay, 1b. So that is how you come up with w and x. Y is the predicted output. X1, x2, x3 are input features. We already discussed. These are the weights and B is the bias. Okay, so that is the initial understanding of all the dimensions of that particular line. And now these are including bias. This is what we have just discussed. W is equal to B into 1. In X, we just added 1. So here we just have added this at the end, and here we have just added this at the front. It doesn't necessarily, if this B comes at the end or before everything, it doesn't really matter. They both are same. Okay. So now you can simply represent this whole equation as y is equal to x into w, right? You can represent y as x into w. You don't have b here because b is incorporated in the weight vector itself. Okay. Now, what is the objective of a linear regression? Linear regression objective is to fit a line where the difference between the actual and the predicted is minimal. Sum of squared residuals should be less. Okay, you're just dividing that with m because you want to just normalize that. You want to see for one point. because for different data sets, you'll have different number of points. So when you want to compare, you just have to make sure you divide that with number of points, so that if one data set has 10 points and if another data set has 100 points, if sum of squared residuals for this will be anyways more, right? Because you have 100 points. When you calculate the sum of squared residuals for the 100 points, that will be anyways more when compared to 10 points. But if you divide this by number of points, you will get the sum of the residual for 1 point. Then you can compare the model performances. That's why you're just dividing that with m. Okay. So the objective of linear regression is to make sure the sum of squared residuals is less. Okay. For a given weight vector, weight vector is the one that decides. Weight vector is the one that decides the direction of the line, right? So what decides the rotation of this line and the intercept of this line? Weight vector. In the weight vector, now we incorporated b as well. So what all we need to find out is the weight vector. So now we need to, the loss function or the objective function of linear regression is sum of squared residuals has to be less. So to do that, what you have to do, you have to derivate the sum of squared residuals. Okay, mean squared error or sum of squared residuals, whatever it is, it's everything is same. Mean squared error, because why we are saying mean squared error? We are taking the sum of squared errors and then dividing by the number of points, right? That's the reason you're getting the mean value there. So that's the reason we're getting some mean squared error. So now this is the equation. So this is the actual predicted, right? Predicted y cap is nothing but x into w that you have seen here. This is the predicted value and y is the actual value. And you're taking the derivative of this objective function with respect to w, because you want to find out the minimal w value. Okay, you want to make sum of squared errors at what w the sum of squared errors is minimum is what you're trying to find out. So you take the derivative with respect to w. So this becomes 2 comes to the front. Okay, so this comes down to be 1 by m into 2 into y minus xw into minus x. So as you're taking derivative with respect to s, this becomes minus x. Okay, so you just, due to dimensionalities, you just add transpose and all that stuff. But x transpose or x, as this is a matrix multiplication, you're just it is just coming down to be minus n. So this all looks like minus 2 by m x transpose y minus x into w. Okay, and then you equate that to 0. Equate the derivative to 0 to get the minimum value. So 2 goes to the other side, it will be equal to 0. M goes to the other side, it will be equal to 0. So finally we will left with x transpose into y minus x into w. As this is a matrix multiplication, you need to expand this. X transpose into y minus x transpose x into w. Okay, and then you shift is equal to 0. You shift this to the other side. This becomes x transpose y is equal to x transpose x into w. So what all you need to find out? You need to find out w. So w is nothing but take this x transpose x into the other side. So that becomes inverse x transpose x whole to the power of minus 1 into x transpose y. So now you find out, you got the value for w. So if you solve this, you will get the weight vector, and that weight vector will give you the optimal line. So this is all what happens within a linear regression. But there is a catch here. Okay, so inverse of a matrix does not exist if this is a singular matrix. If the determinant of a matrix is equal to 0, then the inverse of a matrix does not exist. And when does the determinant of this x transpose x whole to the power of minus 1 will be 0? If there are dependent variables in x. That means if there is an dependent dimensions or linearly dependent dimensions. So these are the dimensions that we have talked about, right? This is dimension, this dimension 2. This is x1, x2, x3, right? So if you take some example, if weight, size, and feed, okay? Feed and weight are dependent variables, right? But what we have considered earlier, everything as an independent variable, right? The earlier assumption is that everything is independent. That's what we have assumed. But feed and weight are dependent. When such dependent variables are there, then if there is a relationship between such variables are there, then inverse of a matrix does not exist. If inverse of a matrix does not exist, we cannot calculate the W. For example, if you take this example X, if the data that is given for us is looking like this, and if you calculate X transpose X here, okay, if you calculate X transpose X, how does this look like? X transpose is nothing but 1, 2, 3, 1, 2, 3. And what is X? 1, 2, 3, 1, 2, 3. And if you take if you calculate this, no, how does it look like? 1 into 1 plus 1 into 1, 2, 4, 6, 4, 8, 12, 6, 12, 18, right? If you take the derivative of this, um, uh, if you take the derivative of this particular matrix, uh, you have to find out what will be the derivative of this. And then this, you'll get that as 0, because derivative will not exist if there if you have one 0 column within it. That means if you just multiply this column with 2, you might have tried this matrix transformations in your engineering, but let me do this. If I multiply this with 2 here, if I multiply the first row with 2, if I multiply first row with 2, this comes as 4, 8, 12. So 2 into 2, 4, 4 to 8, 6 to 12. And the second row is also 4, 12, 8. And the third row is equal to 6, 12, 18. And when you subtract this with this and replace here, and that means R1 is equal to R1 minus R2. This is just a matrix transformation. Once you do that, the top row will always be equal to zeros. So this will give you the determinant of the matrix to be 0. So as the determinant of this matrix is 0, you cannot calculate the inverse of this. Then how do you calculate W in such cases? And predominantly, as we have more number of features, one or the other features will be dependent of each other, right? So how do you calculate in that case? In that case, when X transpose X does not exist due to linear dependence between the variables, that is the matrix is called as singular. Okay, a singular matrix means one of the other columns there is a linear dependency between them. It means that column X are not linearly independent, which results in rank deficit matrix. So the rank of this is not 3, the rank of this is 2. Okay, in this case you can't use the normal equation directly, okay, to calculate the W. In such cases you cannot directly use this equation to calculate the W. In every cases you have to calculate using pseudo inverse of X, okay, using some methods, using like singular value decomposition and all that stuff. The systems will still calculate the inverse of this matrix. So the one such method is to handle this, you have to use a pseudo inverse of X, which can be computed even when X transpose into X is not invertible. Okay, the Penrose pseudo inverse provides a generalized way to find a solution to the least square problems, even in the case of linear dependency. So there are some methods, even though there is a dependency, yeah, inverse of the matrix can still be calculated using some softwares. One such method is singular value decomposition, pseudo inverse of X, and all that stuff. Okay, pseudo inverse of X can also be calculated using singular value decomposition. Okay, this all looks good. Now going back to the next slide. Now, to avoid this problem of not able to uh, calculate the transformation, you have something called as ridge regression. Okay. In the last session when we were seeing the interview questions, you have seen that L1 regression and L2 regression, right? So this is what L2 regression is. Okay. L2 norm or ridge regression, whatever it is, this is called as ridge regression. Let's understand what is the main idea behind this ridge regression and how does this regression will help us, or this L2 norm will help us not running into that singular value, or singular not running into that singular matrix. Okay. So the main idea of ridge regression is to avoid overfitting. Let's suppose if I have only 2 points, okay, and if I am trying to fit a new line to this 2 points, okay, if you look at this, I have only two points here, and for 2 points, I can fit a straight line to them. So there is no harm. So always the minimum sum of squared distance for for these 2 points will be 0. That means we are getting an optimal line. So if these are the training data sets, and if you're getting if the green dots here are the testing data sets, that means the model is performing very well on the training data set, but not on the testing data set, because if you look at these points, the residual is very high for these points. Okay. This means the variance is high. The new line has high variance. You know what is bias and variance. We discussed all that stuff. So for this new line, the variance is high. That means new line is overfit to the training data. So this line is overfit to the training data. Okay. When it is working well on the training data, but not on the test data. To avoid this problem, to avoid this overfitting problem, ridge regression introduces something called as bias. Okay, ridge regression is the main idea behind ridge regression is to find a new line that does not fit the training data. Okay, when you are given only two data points, you will always get the straight line joining those two data points. But what ridge regression will do is it will add a small bias to that particular line, so that it reduces the variance in the out. It reduces the variance. In other words, we introduced a small amount of bias into how the new line is fit the data. So when you're not adding any bias, this is the optimal line that the model is giving to you. Once you added the bias, the line slightly rotated. So once the line slightly rotated, the variance got decreased, right? The variance of this line is the variance of this line is greater than this line. But once we added some bias, the variance got drastically reduced. That means even though there is some bias introduced on the training data set, it is working well or predicting well on the testing data set or on the new data set. That is what our main goal is. Our main goal is not always to do a perfect fit on the training data or performing well on the training data set. The model has to perform well on the testing data set or the new data set. Okay. In other words, by adding a slightly worse fit, ridge regression can provide better long-term predictions. So slightly worst fit. We are not exactly fitting the training data. We slightly moving it by adding some bias. How do we add that bias and all this stuff is what we will see in this slide. So if you look at this, when least square determines the parameters, okay, what we do, we always take sum of squared residuals, right? The distance, I mean, the difference between actual to the predicted is what we take. That is what we take as the sum of squared residuals when you are taking the least squares method. But using ridge regression, along with sum of squared residuals, we add another bias. The bias is nothing but lambda times the slope square. That means weight square. Slope is nothing but weight here. Okay. Slope square is nothing but weight whole square. Okay. Weight is nothing but, let's suppose if you have n vectors w1, w2, w3, modulus of w is nothing but root of w1 square plus w2 square, so on, wn square. That is what lambda of whole square means. Okay, so this is the bias that we are introducing with ridge regression. So this bias will slightly shift the line. Why it is slightly shifting the line is what you will see in the next example. So this part of the equation adds a penalty to the traditional least square. So this is the traditional least square objective function. Objective function is sum of the squared residuals, minimizing the sum of squared residuals. But with ridge regression, to avoid that overfit problem and to reduce the variance, we are you adding a small bias. So here lambda is the lambda determines the severity of this penalty. If lambda is equal to 0, it is same as um, least squares method. When lambda is very high, how does it actually behaves is something that you will see now. So as I told you, once you added this bias, you're slightly shifting the perfect fit a bit. Why is what this example will actually tells you that. Okay, if you look at this, um, if you look at this equation represents this line, this equation represents this blue line. Okay, so when I'm for now I'm considering lambda is equal to 1 for now, and if you take this objective function sum of squared residuals plus lambda times slope square. So what is the sum of squared residuals here? It is 0 because there is the predicted value is exactly same as the actual value because the points lied on the line. So sum of squared residuals is equal to 0 plus lambda into slope square, that is 1.3 whole square. So the total is coming down to 1.69. So now the objective function value for this line is 1.69. Okay, after adding the bias. Now this line is represented by 0.9 plus 0.8 into weight. And now if I have to use this function sum of squared residuals, that means this is the line, this is the sum of squared residuals, right? I need to calculate the difference. This is the predicted value. This is the predicted value on the blue line. This is the actual value. So I need to take the difference and square that. So that comes down to 0.3 whole square for this. This is 0.3, this residual, and this residual is 0.1 square. So this is sum of squared residuals plus lambda is equal to 1 plus 0.8. The slope of this line is 0.8 whole square. So if I calculate this value, I'm getting it as 0.74. Now the objective, for which line the objective is less, which is this object. This object is less for the blue line. So we choose this line as the best fit line with the ridge regression. So when you slightly move this, what happened in the previous screen, the variance got drastically reduced, right? So that is what ridge regression will do. Ridge regression will add a bias to the least squares objective function so that the line will be a slightly worst fit, but it helps for a long-term better predictions. So this is what ridge regression will actually do. Okay. Um, how does this ridge regression will avoid us? But before going there, let's understand here we have set lambda is equal to 1, right? But how do we decide what value for the lambda, what value we have to take for the lambda? Okay, that is decided by doing cross validation. Okay, let's look at how the lambda value will change. Okay, before going further, um, if you look at this, just look at these two lines. The slope of this line is 0.8, right? The slope of this line is 0.8. The slope of this line is 0.8 and the slope of this line is 0.1.3. That means the overfitted slope is greater than this slope. Okay. When the slope decreases, if you look at this particular diagram, when the slope increases, for small changes in the weight, there will be large change in the size, right? That is what high slope means. When the slope of the line is steep, then the prediction is size is very sensitive to the small changes in weight. When there is a small change in the weight, size will drastically change when the slopes are very high. When the slopes are low, and the slope, if you look at this, the slope of this is very, very much lesser than this line. So when the slope is low, for more change in the weight, there is very small change in the size. That means the predictions of size are much less sensitive to the weight. So until unless there is more change in the weight, the size will not drastically change. There will be, for some change in the weight, there will be a very small change in the size. But when the slope is very steep, the size will drastically change with small values in the, with small change in the weight. So now what we understood with this is like, what is ridge regression is doing? Ridge regression is decreasing the slope of the lines, right? So this is the least squares fit. By adding the bias, ridge regression is slightly reducing the slope of the line to increase the variance. That means ridge regression is less sensitive to weight than least squares regression. It can be any parameter. Okay. So you can say ridge regression is less sensitive to the dependent variables when compared to the least squares line. So now, what should be the lambda? Okay. So for larger lambdas, when lambda increases, when lambda greatly increases, the slope will greatly decrease. Okay, when you keep on increasing the lambda, slopes will continuously decrease. Okay, so if this is lambda is equal to 1, when lambda is set to 2, the slope will further decrease. When lambda is set to 3, the slope will further decrease. And now, what would be the ideal value? How to get the ideal value for lambda? Okay, so the larger lambda gets, our predictions of our sizes become less and less sensitive to weight. That means it's always coming down to be like mean. Okay, so how do you decide the value for the lambda? Again, it is cross validation. We try a bunch of values for the lambda using 10 cross validations. You know what is cross validation? 10-fold cross validation also, to determine the value of the lambda, which results lowest variance. Okay, wherever the variance is less, we set that value for the lambda using cross validation. So this is how you determine the value for the lambda. Okay, and now, as I explained this to you, this is what ridge regression is. Okay, and now I also told you that this problem can be achieved by using ridge regression. Now what you are doing, how can we actually achieve this, is what we will see now. So with normal least squares, the objective function is, I'm removing this 1 by m for now because that's just to normalize. So it is y minus x w whole square plus alpha, or you can say lambda. So what you're adding to the objective function, sorry, what you're adding to the objective function here, you're adding to the objective function. What you're just doing is you're adding um, whole square plus lambda into, you're adding weight vector whole square. Okay, so this is the new objective function with ridge regression. Now if you take the derivative of this, what you're going to get here, you're going to get, let's suppose you take the derivative with respect to w, that becomes minus 2 into yi minus xw into x transpose, right? Because minus and minus will become, yeah, that minus will become minus here. So eventually this comes down to 2 to the transpose, 2 into x transpose into y minus xw plus lambda into 2 into w, right? W square is, when you take the derivative with respect to w, it becomes 2w. Now I am removing these two on this side. So this becomes x transpose into y, um, x transpose into y minus x transpose x w plus lambda into w. Okay. So now if you take this to the other side, this becomes 2y minus xw, y minus predicted whole square y square. This is X transpose Y, right? Okay. So now if you look at this, so now what I'm doing, X transpose into Y. Okay. Now if you look at this, uh, this comes down to X transpose Y is equal to, I'm taking these two terms to the other side. X transpose X W minus lambda W. I'm taking W common. This comes down to X transpose X minus lambda. Okay. Lambda. Now, lambda I can say as this is matrices, I can just add I to this. So now W will become, with the ridge regression, W will become X transpose X minus lambda I inverse, right, into X transpose Y. When this is a singular matrix, even though this is a singular matrix, if you cannot calculate transpose for this, you're adding this term. So as you're multiplying, as you're subtracting this X transpose X with minus lambda 0 0 lambda, you will always get the what it is. You will always get the transpose of this matrix. Let's take the same example here. What is X transpose into X will become? We have seen that value, right? What is that? 2 4 6 something. On the other side, let's say this, on the first row we got some zeros, right? And on the second row we got some 4 8 6. On the third row we got something like 8 9 10, something like this. So these are zeros, right? Now this will be added with something like this, 0 1 0 0 0 1. So when you added this became 1. Okay. And now you can never make this turned down to a non-singular matrix. Now there are no dependency between any of these two after subtracting this one. So now if you look at this, even though this is 0, when subtracting this with this identity matrix with lambda value as 1, this becomes 1 0 0 4 7 6 8 9 9. So this there is an there is an determinant existing for this matrix. You get a determinant. Determinant is a non-zero value. So this is how ridge regression will avoid um, not getting a value for W because X, if there is a dependency between the dependent variables. Okay, so that is how ridge regression will avoid this running into a singular matrix for calculating the W. So that is all about for today's session. We started with, I think this is all good. Probability and likelihood is good. We understood maximum likelihood is good. Calculating the normal distribution is also similar. And then we calculated the value for mu and the sigma, the formulas. And then we understood what are odds. Odds is nothing but something happening to something not happening. Whereas probability is something happening to everything that could happen. And converting odds to probabilities is what we have seen. R squared is nothing but how much variance in the independent variable is explained by the dependent variable. I mean, the dependent variable is explained by the independent variable. When R square is equal to 1, there is a strong relationship between, 100% of the variance in the independent variable is explained by the dependent variable. That means there is a strong relationship between those two dimensions. That means like size has strong relationship with the weight of the mice, something like that. And R square is determined by variance of the mean minus variance of the line by variance of the mean. And this can also be written as sum of squares around the mean minus sum of squares around the line by sum of squares around the mean. And then we have interpreted the value for R, and then we have understood what is fitting a line to the data. Fitting a line to the data is nothing but a line which has lowest sum of squared errors um, is the best fit line. And then that method is called as least squares method. But least squares method has a problem of you need to find out a sweet spot between horizontal line, which is the mean, and and two vertical line. You have to find out there will be one sweet spot that fits the data exactly. Okay, and then you have seen uh, um, multivariant normal multi R square for multivariable models. That means when you have multivariable models, and now you have to fit a plane to the data points. Okay, hyperplane. When there are two dimensions, you have to fit a line. When there are n number of dimensions, you have to fit a hyperplane. Okay, and then you have understood what is linear regression, objectives of linear regression, solving for W. When there are dependent variables, inverse of the matrix does not exist. And then to achieve that inverse of the matrix, there are you have to do you have to do that inverse calculation. Even though there are dependent variables, you can calculate the inverse of the matrix by taking the pseudo inverse of X, by using singular value decomposition methods, or by using L2 regression or ridge regression or L2 norm. So what does L2 regression will do is, ridge regression will do is, it will add a bias. So that bias will reduce the variance. That will eliminate the overfit condition. Okay, so that is what we have seen here. It has shifted a line a bit. I mean, it decreased the slope a bit, or it made some worse. It made a little worse fit than the actual fit. And then what happened with that little worse fit? The variance of the data got reduced. That means it is performing well on the training on the test data set too. Okay, and then you have talked about finding the value for the lambda, which is the which determines the penalty, and that lambda will be determined by cross validation. You know what is cross validation, tenfolds cross validation, and all that stuff. It's just shuffling the data and creating different data sets, and then training and testing and finding out and tuning the values for something. And you predict the value for lambda that way. And then we discussed about why ridge regression is eliminate the condition of not able to calculate W from by not by getting X as a singular matrix. By just adding that bias, we are we are making sure the matrix is not singular by just adding this bias to that particular matrix. Yeah, that's all for today, and then I need to continue uh, the next week with ridge regression for discrete variables, and also from R square we calculate F value and P values, which says how much the model, how confident we are with the model that we have derived. And then we have to start um, learning about logistic regression. Do you understand today's session?
Yeah.
Any questions or anything that you want that you didn't understood, or might need better explanation of that sort?
Nothing